with any nonlinear equation, one of the things we'd like to do to solve for the x is to try to factor. So that's what I'm going to try to do for this one. If you've got a product of two things equal to 0, then each of the factors has to be 0. So I have two terms. The terms are separated by this plus sign, and the two terms have a common factor of cosine. So that's what my factoring step will be, just to pull out the common factor of cosine. So when I pull that one out of here, I've got 2 times the sine of x as my first term. And if I pull it out of here, I'm going to have to put a 1 as the placeholder here. So now I take each of the factors and set them equal to 0 and solve for the trig function. The first one says that the cosine of x is 0. I'll come back to that. Then 2 times the sine of x plus 1 is 0. Who remembers in the interval between 0 and 2 pi the values of x that make cosine 0? The angles at which cosine is 0.
Pi over 2 and 3 pi over 2.
Perfect, perfect. X is pi over 2 and 3 pi over 2. For the next one, I'm going to solve for the sine of x by subtracting 1. And then I'm going to divide by 2. The sine is a negative number. Remember our little saying, all students take calculus. It says all of the trig functions are positive here. The sine and 1 over the sine is positive here. Tangent 1 over the tangent is positive here. Cosine and 1 over cosine is positive there. Turn that. I'm supposed to be able to do that with this one. That's not the, that's one that has the X on it. I think I'll just try. I'll try not to write that far over. Okay, so what this is telling me is I've got to come up with angles in quadrant 3 and quadrant 4. So to get the angle in quadrant 3, I'm just going to take pi and add my reference angle. To get the one in quadrant 4, I'm going to take 2 pi and subtract my reference angle. So the reference angles again were the ones in the first quadrant. Let me redraw this table. Let's see, I was going from 0 to pi halves in smallest to largest. So 0, pi 6, pi fourths, pi thirds, pi halves. And let's see, it goes 0, a half, square root of 2 over 2, square root of 3 over 2, 1, and then the other way. Remember these, then we can use that to get our other angles. So that's square root of 3 over 2, and now 1. So what this is telling me is I've got to use pi over 6 as my reference angle. So the two solutions to this equation are x is equal to pi plus pi over 6, and x is equal to 2 pi minus pi over 6. So let's think of pi as being 6/6. So 6/6 minus 1/6 gives me 5 pi over 6. And then 2 pi is 12/6 pi. 12/6 pi minus 1/6 pi puts me at 11/6 pi. So we have 4 solutions to this equation. Yes?
So is the first one that pi plus pi over 6 or minus pi over 6?
To get me in quadrant 3, I need to go pi plus pi over 6. Okay? Because the sign is going to be negative here. So I have to move pi over 6 further than pi.
Okay.
And then here I had to back up pi over 6 from 2 pi. If we need a reference angle in quadrant 2, that's where I would subtract. And all of these angles are the ones that I'm referring to as theta. Okay.
That would be 5 pi over 6 or 7 pi over
Oh, so I added wrong. So there's that. There's that. Thank you. Numbers. Any questions on that one? Okay, let's try the same idea with the next one. And the next one is a tangent function. So if you want a tangent, let's do sines over cosines. Let's just increase this table. That's why I always put it in this order, since tangent is sine over cosine. So I'm going to take 0, divide it by 1, and get 0. I'm going to take 1/2 and divide it by the square root of 3 over 2. Let's do this step in our head. We're going to take this, flip it over and multiply. So I have 1/2 times 2 over the square root of 3. The 2 on the bottom, the 2 on the top cancel. So I have 1 over the square root of 3. This one I have the same numerator and denominator, so that'll simplify to 1. This one will be square root of 3 over 2 divided by 1/2. So again, do the flip and multiply step, and the 2's cancel, and we just have a square root of 3. And what happens here when I divide by 0? 1 over 0, what do I write here? Undefined, right? So there's not a value there. That's where that asymptote is for the tangent function. Okay, so in the next one, we've got square root of 3 times the tangent of x is equal to 1, and we want again the x's between 0 and 2 pi. So we don't have to factor, I just have one trig function. This would be kind of a version of a linear equation, linear and tangent. Get the tangent by itself by dividing by the square root of 3. My little diagram over there tells me the tangent is positive in quadrant 1 and in quadrant 3. So I need the quadrant 1 from the table and the quadrant 3 by taking pi plus whatever angle I have up here. In quadrant 1, I look over here. This occurs when theta is, or when x is pi over 6. So here I add pi over 6 to pi, and this time I can do it right. And there's our other x. Is that okay with you? Okay, what did we say about inverse functions? Let's back up and talk about inverse functions. I'm on problem number 11. I think we did problem number 11, didn't we? We did not. No? Okay, so suppose you have a function f that takes x to y in such a way that f is a one-to-one function. One-to-one function has the property that each x has only one y, and each y has only one x. If f is a one-to-one function, then there is an inverse function that takes these y's back to those x's. So then F has an inverse with the property that if the ordered pair AB is on the graph of F, then it goes the other way, is on the graph of F inverse. Takes the ordered pairs and swaps them. Or if I call this Y F of X, what F inverse does is it uses F of X as the input and it spits back X. It works the other way as well. If I do the composite function with F inverse of some dummy variable in there, these two rules peel each other off. And this tells us how to find the inverse. If you have the rule for F, change the X and the Y and solve for the Y. So let's look at number 11. Number 11, we have F of X is a rule that takes an input, multiplies it by 4, and then subtracts 12. What's the graph of this function look like? Just a line, right? Line with the slope of 4 and y-intercept of 12. Or negative 12. So if this is the ordered pair, 0, negative 12. So let's see if I break that up into, those look like they're about 4, maybe. So if that's 4. Let's see. If X is 3, Y is 0. Anybody see that? So if this is 4, then this would be the ordered pair 3, 0. My line looks like that. What makes it 1 to 1 is that every time I pick a Y value, just pick any Y value and run a horizontal line, I find only one X. We have a horizontal line test for 1-to-1 functions. The inverse is a function that takes the ordered pair 3, 0, swaps it, and gives me the ordered pair 0, 3. Takes this ordered pair and plots it back here. So this would be the inverse, another linear function. The instructions are to find the rule for that inverse. So what we do is I make this Y value into an X, make that X into a Y, and solve for Y. So find F inverse, make Y into X, X into Y, and solve for Y. Is that something you've done in the past? Stuff you remember? So that's the X now, that's the Y. Peel the stuff away and get the Y by itself. So I add 12, divide by 4. So if I want to emphasize that I have a linear function, and I'm going to change Y now to F inverse, I'm going to say that it's 1/4 X plus 3. So there's that y-intercept of 3, and now the slope is 1/4. Okay. All right, so next one's your turn. This function, number 12, is not 1-to-1. F of x is 4 minus x squared. What is the graph of that thing? Which way is this parabola open? It opens downward, doesn't it? Because of the minus in front of the x squared. The y-intercept is the vertex at 0, 4, since I don't have an x to the first power in here. So this function is not 1-to-1. It goes through 0, 4, and then when x is 2 or -2, it crosses the x-axis. Not 1-to-1, so what I did is I cut it off for x negative. So I'm going to cut the parabola in half and keep only the negative x's. So the inverse of this function is going to go through the ordered pair 0, -2. And I'm going to take this one and move it down to 4, 0. And it's going to go through those 2 points. There's the graph of F inverse. Remember, it looks like the reflection of the graph about the line y is equal to x. Now find it. I'll give you about 2 seconds. Make the y into an x, the x into a y. Let's see if you can find the rule for F inverse that gives me the bottom half of that parabola. Got it? We put an x where the y is, and a y where the x is. So I'm going to solve for y. I'm going to swap places with these guys. I'm going to add y squared to this side, subtract x from that side. So I get y squared is 4 minus x. And now I'm going to take square roots. Which of these square roots guarantees that part of the graph? Negative. All the y's are under the x-axis, so I need the negative square root. So my inverse is minus the square root of 4 minus x. So to make a quick check, if I put a 4 in for x, I do get 0. If I put a 0 in for x, I do get -2. Okay. Now, what I showed you last time is none of our trig functions are 1-to-1. So I think we restricted the domain of them. Did we do that already? Okay. So we defined our inverse trig functions. Our trig functions take an angle. So some number between 0 and 2 pi and more, and give us a number between, say, 1 and -1 for sines and cosines. The inverse sine and cosine takes a number between 1 and -1 and gives us an angle in a designated region. So let me rewrite where those regions are. inverse trig functions for y is equal to the sine of x. We had to restrict those x's to be angles between minus pi over 2 and positive pi over 2 to give us y values between -1 and +1. So we're talking about those angles. We define the inverse sine of that number, but I'm going to change it to an x and make that a y. Inverse sine of that number is a number y, where that number is between -1 and 1. And that number is between -pi over 2 and +pi over 2, with the property that the inverse sine of x is a number y if and only if, let me take that out of here, if and only if the sine of that number y gives us back x. For the inverse cosine function, we restricted the domain to be between 0 and pi. And we said that the inverse cosine of a number between 1 and -1 is an angle if and only if the cosine of that angle is that number, where again, x is between 1 and -1, and y is between 0 and pi. And then for the inverse tangent, we kept it between -pi over 2 and pi over 2, and to find the inverse tangent of a number, any number, to be an angle between -pi over 2 and pi over 2 that I would take the tangent of to get that number. So x can be any real number, but these angles are strictly between pi over 2 and -pi over 2. And we did something like this. We found those angles. I wanted you to find, say, the inverse sine of 0, the inverse sine of 1, the inverse sine of -1, and then I like the halves, +1/2 and -1/2. We did that last time. Let's see if you can quiz yourself and remember. What angle do we take the sine of to get 0? Sine of 0 is 0, so the inverse sine of 0 is 0, because the sine of that angle is that number. What angle in that interval do I take the sine of to get 1? Pi over 2? Good. So what angle do I take the sine of to get -1? But not 3 pi over 2, it's got to be -pi over 2. Acute angles that way or that way. Sine of what angle is a half? We just did that one a second ago. Pi over 6. So to get a negative 1/2, I have to go backwards to negative pi over 6. If I plot those points now in the XY plane, these are the X's, those are the Y's. These numbers here have to be between 1 and negative 1. And the numbers on the y-axis are between pi over 2 and negative pi over 2. Pi is 3.14, so if I divide that by 2, that's like 1.57. So if that's 1, then my top y value is about here. That's pi over 2. This graph passes through the origin 0, 0. It passes through 1 pi over 2, negative 1, negative pi over 2, and then 1/2 pi 6, where pi 6 will be a third of the way to pi halves. So I kind of eyeball it to about right there, and then the negative. And the graph of the inverse sine function is going to look like this, with no arrows on it. To get the graph of the inverse cosine function, let's find the inverse cosine of those same numbers. I want the inverse cosine of 0, the inverse cosine of 1, the inverse cosine of negative 1, the inverse cosine of 1/2, and negative 1/2. But this time you're going to give me angles here. Quadrant 1, if the number in the parentheses is a positive number. Quadrant 2, if the number in the parentheses is a negative number. So we start out with the inverse cosine of 0. That's the angle that I take the cosine of to get 0. Cosine of what angle is 0? Pi over 2. Cosine of what angle is 1? 0. Cosine of what angle is negative 1? All right, good. Cosine of what angle is 1/2? Spot you the pi over 3. So now you've got to give me that. Use that as a reference angle and get me in the second quadrant so that I know the angle that I take the cosine of to get a negative 1/2. 2 pi over 3 is correct. I'm going to plot those points. Notice that they're all positive. They're all going to have as the range y values between 0 and pi. So when I graph them, I don't need anything down here. I do need to go between negative 1 and 1. So I want to go between 0 and pi, so my scale's going to be off a bit. Let's make that pi. And then that's pi over 2. The inverse cosine of 0 is pi over 2, so that's the ordered pair 0, pi over 2. Inverse cosine of 1 is 0. Inverse cosine of negative 1 is pi. The inverse cosine of 1/2 is pi over 3. So if I ignore that pi halves and cut this stick up into 3 equal pieces, then pi over 3 might be somewhere around here. So if that's pi over 3, negative 1/2 is up here at 2 pi over 3. And the graph looks like this snippet. Just a little curve down, curve up kind of thing. No arrows on it. And then quickly, let's get the graph of the inverse tangent. The inverse tangent has the same range as the inverse sine. So if this number is positive, you give me an angle in quadrant 1. If this number is negative, you give me the opposite of that quadrant 1 angle. These numbers are between pi halves this way, negative pi halves that way. On the graph of the tangent function, negative pi halves and positive pi halves were vertical asymptotes. On the graph of the inverse tangent function, those are going to be horizontal asymptotes. And so, to get the graph of the inverse tangent function, let's find some easier values. Let's see. Let's find the inverse tangent of 0, the inverse tangent of 1, the inverse tangent of -1, maybe just for fun, the inverse tangent of the square root of 3. Did that just make it more fun? Okay, here's where you come in. What angle do I take the tangent of to get a value of 0? 0. Tangent of 0 is 0, so the inverse tangent of 0 is 0. Tangent of what angle gives me 1?
Pi over 4.
Good. So what about -1? Negative pi over 4. Just go backwards the way you do like the sine. All right, where does the ratio of sine over cosine simplify to the square root of 3?
Pi over 3.
That's right, I'd have to have sine equal to the square root of 3 over 2, cosine equal to 1/2. And if you look quickly at that chart, that occurs at pi over 3. Here's the graph of the inverse tangent function. It has as its range numbers between pi halves and negative pi halves. So I need to get that out of the way. So let me put pi halves here and negative pi halves there. Those become horizontal asymptotes. Goes through the origin because of the 0, 0. Pi fourths is halfway through here, so if that's 1.7, 1 is about right here. So it goes through that, and then pi thirds is, yeah, who cares? I don't want to do those anymore. It's going to look like that. This is a graph you should remember because we use it a lot in Cal 2. Cal 2, we talk about things that have asymptotic behavior. So this shows that when x gets real large, the inverse tangent goes to pi halves. When x gets real small, the inverse tangent goes to negative pi halves. These are trig functions that reduce the pairings, and they are inverses of one another. So they have the property that the sine of the inverse sine of any input is that input, provided it meets this criteria. And the inverse sine of the sine of any input is that input, provided it meets that criteria. And the same for each of these. The cosine of the inverse cosine of any input gives you back. Inverse cosine of the cosine of any input gives you that back. Same with tangent, I won't even write it again, just wasting my ink. So practice on the next list of angles, and we're going to do this with numbers all the way through, I guess, let's go through part E. Those are all values in our table that I put up here of angles that we know. We've done most of them. Some of them, let me put them all up here. Remember that we can write inverse cosine as an arc cosine, and that's the way we'll write it with all of the trig functions on web work. Instead of using a superscript of -1, type in the arc whatever. Arc cosine means inverse cosine, arc sine means inverse sine, etc., etc. You don't have to remember the other ones. There are inverses of them over other domains. If you can remember these, then you can remember that the arc secant of any angle can be found by knowing the arc cosine of 1 over the or of any number is the arc cosine of 1 over that number. And so if you stick with that, then you can figure out those values. The same is going to be true with all of the other co-functions. The arc cosecant of any number is the same as the arc sine of 1 over that number. And the arc cotangent of any number is the arc tangent of 1 over that number. So if I want the arc secant of 2, I just find the arc cosine of the half. All right, so on number 13, you're going to do parts 1 through E for me while I write them down up here. We've done some of them already. I think we've done them all. And I'll pick it up from part F. So I've kind of erased them. We've got the first one. The arc sine of 1 was pi halves. The arc cosine of 1/2 was pi thirds. The arc sine of -1 is negative pi halves. But the arc cosine of -1/2 was 2 pi thirds. And now here we could work our way inside out. We do the inside first. Over there, we said the arc tangent of 1 is pi fourths. And now you're going to tell me what the sine of pi fourths is. So the sine of the arctangent of 1 is square root of 2 over 2. Is that straightforward enough? Did I do that too fast? Just an instant replay of what we did a second ago. Now, when there's a number inside here that we don't recognize as one of our reference angles, we just use the fact that those represent angles. Inverse trig functions are angles in the specified range. So for instance, for part F, I want to find the cosine of the angle that is the arc sine of 1/3. One-third is not one of the numbers that I know from my table. It is a number between 1 and -1. So there is an angle there. It's a 1-to-1 function. When I drew you that graph of that inverse sine function, there were no jumps in it. So it does pass through 1/3. I don't really need to know the angle. One of the lessons in trig is that if you know the value of one of the trig functions of an angle, you know all 6 of them, because we have right triangle trigonometry. This inverse trig function represents an angle. So I'm going to say, let's let A be that angle. Since that's a positive number, I know that angle is in quadrant 1. And it's an angle in quadrant 1 that I take the sine of to get 1/3. And so I'm looking to find the cosine of that angle. I'll make you a quick picture. Here's a right triangle in quadrant 1. There's angle A. This is describing the ratio of 2 sides of this triangle. Which 2 sides? Opposite over the hypotenuse. In order to find the cosine of that angle, I need the adjacent side. So you're going to whip that out with the Pythagorean theorem. Let's do it. Find the length of that adjacent side. Leg squared plus leg squared is hypotenuse squared. Everybody get square root of 8? You don't have to rationalize or simplify or anything like that. I have hypotenuse squared is leg squared plus, say, the other leg squared. So 3 squared is 9. That gives me 8. So a little a is the square root of 8. And so the cosine of the arcsine of 1/3 is the adjacent over the hypotenuse. Square root of 8 over 3. That make sense? All right, all right, all right. In part G, I put a little twist in it. I got a 2 right here. Then I've got an angle. Our cosine of 4/5. So I'm going to start the same way. I'm going to take my inverse trig function and replace it with an angle. So I'm looking for the sine of 2 times that angle, where that angle has the property that when I take the cosine of that angle, I get the ratio 4/5. So I can draw that triangle real quick. Cosine is adjacent over the hypotenuse. Does anybody recognize what length the other side has to be? 3, 4, 5 triangle. 5 is the hypotenuse. Okay, but I can't just say that this is 2 times the sine of angle A. Trig functions don't behave algebraically where I could just factor a number out of here. There's an identity that goes with this. Does anybody remember the double angle identities for our trig functions? I do. We're going to need a double angle formula for part G. We're going to need a sum formula for part H. So here's the double angle formulas. The sine of twice an angle is 2 times the product, the sine of the angle and the cosine of the angle. The cosine of twice an angle is the cosine squared of the angle minus the sine squared of the angle. The tangent of twice an angle is the sine of twice an angle divided by the cosine of twice the angle. Our sum formulas are the sine of A plus B looks like sine of A cosine of B plus cosine of A sine of B. If this has A minus B here, they'll just change that to a minus. The cosine of A plus B looks like cosine A cosine B minus sine A sine B. And if there were a minus here, then this is a plus here. You don't have to memorize those, but by the time you get through calculus 2, you will have them memorized because you use them so much. I'll give those to you if you ever need to use them. They're on the little handout of trig identities that we'll use this semester. So we're going to use the top one right now. The sine of twice an angle is 2 times the sine of the angle times the cosine of the angle, and that's the angle represented in the picture. That picture tells us that the sine of A is 3/5, and we just said below the cosine of A was 4/5. So the sine of 2A is 2 times 3/5 times 4/5. You multiply fractions, multiply all the way across. So I'm going to get 6 times 4 is 24. over 25. Okay. Too fast? Okay, so for part H, part H. Go ahead and erase. I have the sine of two different angles. I have the arctangent of the square root of 3, and the other angle is the arc cosine of 4/5. Since they're two different angles, I'll use two different letters. I'm going to call this one angle A and that one angle B. So you're looking to find the sine of A plus B, where angle A has the property that the tangent of that angle is the square root of 3. Angle B has the property where the cosine of that angle is 4/5. So it has the same picture as this angle A over here. Cosine of angle B is 4/5. It's just what we did a second ago. We can draw a triangle with this one, or you can use the fact that that's a known angle, an angle that we have in our table. What is angle A? What angle do I take the tangent of to get the square root of 3? Pi over 3. So A is pi over 3. That's all I am today. My vegetables. So we're actually looking for the sine of pi over 3 plus b, which is not the sine of pi over 3 plus the sine of b. The sine of pi over 3 plus b is the sine of pi over 3 times the cosine of b plus the cosine of pi over 3 times the sine of b. So I'm going to expand that now using our identity. I'm going to use the picture to give me the sine and cosine of b. I'm going to use my noggin to give me the sine and cosine of pi thirds. Well, your noggin, what's the sine of pi thirds? Funny person. Cosine of b we know, cosine of b is 4/5. Cosine of pi thirds? Half. Sine of b from the picture is 3/5. So I get 4 square root of 3 over 10 plus 3 over 10. So I can write that as 4 square root of 3 plus 3 all over 10. So does that remind you of perhaps the last web work problem or somewhere down there? Think you're able to do that now, or do you want to work it together in class? You want to try it? Do you remember it? Didn't you ask me about it? And I said maybe you didn't ask me about it. Is that the same deal as at inverse trig? No? Somebody asked me and I said I'd do it today. You asked me.
Yeah.
Do you remember the problem?
No, I can pull it up.
Well, you can't make it up. Pull it up then. Let's work it together. What time we get out here at 12:15? I wanted to start chapter 2. I'll just talk real fast. Let's try that web work problem together. When is this first web work due? Tonight? But nobody asked me any questions? Got it?
Yeah. It's the cosine of 2 tan 2 on 10. And x over 4.
Okay, so numbers aren't special. We can do all the same stuff that we did a second ago with any expression that I'm taking an inverse trig function of. So the inverse trig function represents an angle. And the instructions are to find the value of this strictly as an algebraic expression in x. So I'm going to have some version of this, but there's going to be x's in it. So I start by saying, let's take the angle to be the arctangent of x over 4. That means the tangent of that angle is x over 4. Then your job is to find the cosine of twice that angle. So you need the identity that I just erased. Cosine squared of the angle minus sine squared of the angle. So here I'm going to cut you loose for a few minutes. You're going to draw a right triangle so that the ratio of the appropriate sides is x over 4. You're going to find the third side. Once you find that third side, you're going to use the triangle to find the cosine of angle A, and then you'll square it. Then you're going to find the sine of angle A, and then you'll square it, and then you'll subtract. So draw the picture, fill them in, and then I'll come back at you. Here's where you're starting. There's an angle A. Which two sides do we have going on here with the tangent? Opposite over the adjacent. Then leg squared plus leg squared is hypotenuse squared. So leg squared plus leg squared is the hypotenuse squared. So the hypotenuse is the square root of that. And just a little warning, the square root of 16 plus x squared is not 4 plus x. Right? I'll leave it just like that. Okay. So now you need the cosine of that angle, and then we'll square it. Then you'll need the sine of that angle, and then you'll square it. All right, using this picture, what's the cosine of this angle? Or over that guy, right? And this one would be x over that guy. Everybody okay to that point? When you square a fraction, you square the top and square the bottom. When I square the bottom, I just lose the radical sign. So I'm going to have 16 over 16 plus x squared. Here I'll have x squared over 16 plus x squared. And they have the same denominator. I can write them as a single fraction. And so I get 16 minus x squared over 16 plus x squared. Is that what you got? While we're on web work, can you think of anything else you want to ask about? Anybody, anywhere, anyhow? Not shy, are you? How do I know if you're shy? You're just ready to start some calculus. Get out of this pre-calculus junk. All right, so I think of our calculus part of the course as being broken up into 3 clumps. The first clump are the basic concepts of calculus of limits and continuity. The second one will be derivatives and application of the derivative. And then the third one will be antiderivatives and applications of the antiderivatives. Both derivatives and antiderivatives come from limits. So we need some sort of idea of what a limit is. In calculus, unlike in trig, calculus is interested in things happening over a continuum. The variables that we're talking about, the x's and the y's, are defined for all values. Where our trig functions, they represent some instant in time, a little triangle maybe, or point on a circle. So in this continuum, we can think of things moving around on graphs. We've got x values and y values. And the question is, can you tell me what the graph is going to do if I pinpoint an x value? Well, sometimes you can, because they're graphs of things that we know. If you have a straight line and I want to know what's happening in a neighborhood of, say, x is 2, you can just look at the y values on that line. But if you have a weird graph that might have a jump in it or a little bitty tiny hole in it, then you have to kind of mess around with it. So in a limit, we're looking at what are y values when x is real close to a particular number. Maybe I'm a scientist and I want to know what my reaction of some sort of chemical experiment, what's going on in this reaction if this were in, say, on Mars. Well, I can't go to Mars. Nobody has been to Mars yet. But I know maybe what the atmospheric pressure is there. So I take my chemical reaction and I stick it in my little apparatus in which I can adjust the atmospheric pressure. And then I start adjusting, maybe I want it at air pressure 0. So I have my reaction, I have it in my little thingamabobber. See, I'm like a real scientist. I have all the words just right. I put it in my little thingamabobber and I start changing the air pressure so that it's getting closer and closer to 0. And I've got some sort of other thingamabobber in there taking readings. And it's spitting out information. So the closer I get to 0, my information is getting close to some particular number. So I have my input variable, which is the atmospheric pressure, and my output variable is the readings that this experiment is giving me. if as I get this closer and closer and closer to air pressure 0, these numbers are all behaving in a certain way, then my hypothesis is, well, at air pressure 0, this value will be equal to that number. That's what we're doing with a limit. Okay, so in section 2.1, we're going to look at limits intuitively. But we'll see there's a link to doing limits intuitively with doing limits maybe algebraically. So we are interested in values of some particular function when x is real close, and I mean close, to some number a. If these values can be made infinitely close to a particular output, then we say that the value of the limit of that function as x goes to a is equal to the output. So if f can be made infinitely close to some number L, by choosing x near a, then we say f has limit L as x goes to a. So it's a picture. It's a picture. Here's the XY plane. Here's my number a. I'm looking at y values. So here's my y values. There's my f of x's. And so I'm going to just start plotting values. So I know f does this out here. What's going on in here? And maybe it does something else out here. So I take the formula for f and I start plotting numbers. And maybe I'm finding when I plot these numbers that I'm getting this thing to do, I don't know, maybe some sort of wiggling action up there. So I take these numbers and I plug them in and they do something like that. So I plot a few more. These are coming in. They look like they're going to hit. Maybe there's a y value at a, maybe there isn't. But if I can make those real close to where that hole is, I go over here and I measure it, and there it is. So I'm looking at getting these y values real close to that one when x is in this little interval here. So we would write that the limit, you abbreviate that by just knocking off two big old letters. The limit of my function as x goes to a is that number L. And it means this. Just that in math, we don't like to use words. So here's how we write it in math. The limit of f of x as x goes to a is equal to L means that f and L are really close to each other. The distance, absolute value, between f and that y value L is smaller than some real teeny tiny number. I'm using the Greek letter epsilon. Whenever the distance between these two numbers is smaller than another number. I'm going to use the Greek letter delta. If you can find this number by me doing this, then that function has a limit. These two guys are close whenever I make those close. So here's my delta interval. And here's my epsilon interval. Okay, so this is epsilon. Epsilon, maybe? Maybe I spelled it right. I'm not Greek. This is delta. If we have some knowledge of the function, then we can make pretty good guesses of what those y values are. Like, for instance, if I want to know the limit as x goes to, what's your favorite number? 6 on this particular graph. Well, I know exactly what that graph looks like. 4x plus 6, that's a line. There are no breaks, jumps, or holes in it. 4x plus 6, y is equal to 4x plus 6 is a line, right? There's my f of x. I'm sorry, 4x plus 5. That's just a line. So when x is near 6, all of my y values are near that y value that occurs when x is equal to 6. What is that y value when x is equal to 6? 29. So since that y value there is 29, all the other ones are going to be real close to 29. Right? Because I know what that graph looks like. All right. Maybe I don't know what that graph looks like. And I want to know what happens, say, let's go with the limit as x goes to, let's see if I've got any numbers that I can crunch with you. Oh, has to be quick, has to be a quickie. I need a quickie. Have any numbers written down? I do not. Number. I don't. So we make it easy. Let's take the limit as x goes to 1. This one's not as easy because it's not a linear function. It's not a function that I know has a y value at a particular point, because if I try that same trick and try to find the y value when x is 1, I got a little problem. I get 0 on the bottom. I get 0 on the top as well. When x is 1, I get that. That doesn't mean 1. And it doesn't mean it's infinite. It's something in math that we call an indeterminate form. So what I want to do, but I'm not going to do because of the time constraint, is I'm going to pick numbers near 1 and I'm going to plug them in for x. Like maybe if, let's just make a table of values. How about if x is 0.9? Then I'd get out my calculator and I'd compute 0.9 cubed minus 1 over 0.9 minus 1. And I would get, let's see, that'd be a negative 0.1 on the bottom. And did I bring the phone with me? I must have, because I was listening to music. Calculator, where's that calculator hiding? Who even uses a calculator? That should be, all right, turned. I need 0.9 cubed minus 1.9 to the third power. Okay, buttons, where are you? And then take one away. So I get a negative 0.271. If I divide that by 0.1, I just lose the decimal and I get 2.71. So I pick a number closer, like 0.99, and I do the same thing. And I do the same thing, and I keep doing that. And I want to look at what happens as I squeeze these numbers closer to 1. So that's what we're going to do next time. We're going to do it by seeing if there's a pattern of y values as I squeeze my x values closer and closer to 1. And that's not the recommended way to find limits. That's the intuitive way to find limits. Okay? All right, so we'll do that on, what is today? Is today Wednesday? Do that on Friday. We haven't had a Monday together yet. All right, don't trip over my cutoff board. You guys at home okay? Anybody want to ask a question at home? Don't trip, don't trip, don't trip. Okay, if you're not going to ask any questions, I'm going to call.